So this is the most useful theorem we'll have about finite extensions. So let K be a finite extension over E. What that means is K is a field that contains the field E, and you can additionally think about K as not only a field, but simultaneously a vector space over E, which is finite dimensional. That's what a finite extension means. E is also a finite extension over F, again meaning that E is a vector space over F with a finite dimension. Then this property holds. This notation is the dimension, so this notation here, this denotes the dimension of your vector space K over the field F. So the dimension is the number of vectors in a basis. All right, let's prove the theorem. So we're talking about dimension here. This is a statement about dimension of vector spaces. That means we should look at the number of vectors in a basis. So I'm going to start with letting alpha 1 through alpha n be a basis for E over F. And how about beta 1 through beta m, a basis for K over E. So I'm saying that I have n vectors in a basis for E over F. That's what this means. So this thing here I'm saying is n. And I have m vectors in a basis for K over E. So this here is m, is what I'm saying. So I hope that I have m times n vectors in a basis for K over F. So here's the claim. I claim that the set alpha I beta j, where I could be any number between 1 and n, so you could pick any vector, any element in the field you want here, and multiply it by any choice of beta. So you multiply all possible alphas with all possible betas in every possible combination. And I claim that when you do that, you get a basis for K over E, or excuse me, F. So I'm claiming that something is a basis. If this was a basis, then the theorem would be proved because there are m times n elements that I'm listing here. So to show something's a basis, I need to prove that these elements are linearly independent and span. So let's do that. Linear independence. So let's say that we have some linear combination. So let's go j going from 1 to m, I going from 1 to n, Cij, alpha I beta j equals 0 for each Cij in F. So what I've just done is I took a linear combination of the terms in my potential basis and set it equal to 0. I hope, if these vectors are linearly independent, that the only possibility is that all my coefficients, Cij, have to be 0. Then I have linear independence. So we have, though, that this sum is the sum j going from 1 to m. I have the sum I going from 1 to n, Cij alpha I times beta j. That's this same expression. That's equal to 0. And alpha 1 through alpha n are elements in E. So this term in the parentheses for any given j, these coefficients of beta j are in E. Now, beta 1 through beta m is a basis for k over E, meaning that beta 1 through beta m are linearly independent. So that means that the individual coefficients all have to be 0 because they're linearly independent. So it's the sum I going from 1 to n, Cij, alpha I has to be 0 for all j. Now, alpha 1 through alpha n, these are linearly independent because they're a basis for E. Therefore, Cij is 0 for all I and j. So I'm just using the fact that beta 1 through beta m is a basis to get these sums to equal 0. And then I'm using the fact that alpha 1 through alpha n is a basis to get each individual coefficient to equal 0. So that verifies that these vectors are linearly independent. Now, just to clarify, I said vectors here because I'm using the term vector and elements in the field interchangeably. I know it's a little mind-blowing at first, but you got to get comfortable with it. I could both have a field and a vector space simultaneously. Okay, let's do span. Span. So I did linear independence, let's do span. So to do span, I'm going to take an element k in my vector space, capital K. Now, beta 1 through beta m is a basis for k over E. So I could find constants such that k is C1 beta 1 all the way up to Cm beta m. These constants, C1 through Cm, these are in E. So I'm using the fact that these vectors beta 1 through beta m span k over E. But then, since I have elements in E, the constants in front, and alpha 1 through alpha n is a basis for E, I can express each one of these constants as linear combinations of alphas. So I could say that this is, C11 alpha 1 plus C1 n alpha n times beta 1. I'm expanding that constant C1 as a whole linear combination of alphas. You could do this for each term, so I could get Cm1 alpha 1 up to Cmn alpha n beta m. And if you expand everything out, you indeed have k, a linear combination of terms in your potential basis. So that proves span. So now I've shown that they're linearly independent and they span, so I think I'm done. Thus, we have a basis. Okay, join me in my next video for examples, nice examples of this theorem.